let's continue our discussion on advanced dimensionality reduction techniques. By the end of this topic, you will be able to explain and implement backward elimination technique of dimensionality reduction. Backward elimination is used when we are more concerned about removing the redundant variables from the model. It is to strike a balance between the model performance and model simplicity. Let's try to understand this procedure in an easy step-by-step approach. Step 1. We build a model with all the independent variables. The adjusted R-square corresponding to this model will be starting or a baseline adjusted R-square value. Step 2. Drop one independent variable at a time and train the linear regression model using the remaining independent variables. Calculate the corresponding adjusted R-square. Repeat this process for each and every independent variable. Step 3 is to subtract the baseline adjusted R-square from all calculated R-square and record the difference. Step 4. Make the maximum difference value as the new baseline adjusted R-square and permanently drop the independent variable corresponding to it. Step 5 is to repeat the process for the required number of times, which is equal to number of independent variables we want to be left remaining after the completion of this procedure. Now I want you to sit back and think for a moment. What range of values can the difference between the calculated and the baseline adjusted R-square take? And which one is more favorable? Case 1. Calculated adjusted R-square minus baseline adjusted R-square is greater than 0. This means that dropping that corresponding variable actually improved the model, which is exactly what we want. Case 2. Calculated adjusted R-square minus baseline adjusted R-square is less than 0. In this case, the removal of the independent variable decreases the model performance. Therefore, this case is often considered a good point to stop the backward elimination. As we saw in the process, the independent variable corresponding to the maximum difference are eliminated at first. As a result, it is guaranteed that redundant variables are always eliminated first. Now, let's implement the backward selection in Python. This is our second run through the complex code, so hold tight. We will now begin defining the backward elimination function. This function takes 4 parameters as input, that is model x, y, and minimum features. These parameters are exactly the same as the forward selection except for the last one, which is the min features. Here, we need to specify minimum number of features that we need to keep. Now before we start working on the backward elimination, let's initialize some variables which we will be using. First is elim_data. In elim data, we will copy all the columns of xtrain. Next is r2_history. This is to keep track of the adjusted R-square score whenever a feature is eliminated. Next is base_r2. It is the baseline adjusted R-square score when all the independent variables are used to build the linear regression model. Now coming directly to the line 19. We will run this process until we have the minimum required features, which is number of columns in X minus the number of features required. In line 21, we will initialize the variable difference as -100. In line 23, we will start iterating through the different columns of the independent variable. Now in any given iteration, we are dropping a column from the elim_data and copying the resultant data as tmp. Now this tmp data is passed to the return r2 function along with the target variable and the model. Once the r2 variable of the model is calculated, we compare it with the baseline r2, which we have defined in line 27. If the difference between r2 and the baseline r2 is greater in the value than the previously encountered difference, it means that dropping the column in that iteration had the maximum desired effect. Therefore, we do the following updates. We update the value of the difference to the new one. We store the name of the column that was dropped in the variable eliminate. We also store the value r2 into new r2. At the end of a cycle, at line 32, we drop the column stored in elim_data permanently. We also store the adjusted R-square score corresponding to the model built using the data after dropping the column, and also update the base_r2 to new_r2. Once the whole operation is completed, we return 3 things, just like we did in the forward selection, which are current adjusted R-square score, adjusted R-square score history, LM underscore data with surviving columns. Now that we have defined the function, let's call it by passing the same parameters as before, except we are specifying that we need at least 15 columns. So let's run this cell. We can clearly see that iterative elimination of the independent features and the corresponding adjusted R-square score after removing them. We can clearly see that even after removing almost half of the features from the total independent variables, the adjusted R-square score has gone down only by a few points. This verified our assumption of redundant columns being present in our dataset. In case you are struggling to understand this code implementation, we have provided the Jupyter notebook with this code at the end of the topic. Please spend time going through each line of the code and try to understand what is happening there. With a bit of thinking, you would be able to figure this out yourself. So far, in both forward and backward elimination, we gave the number of features we want in the final model as an input. But let me ask you, is there a more appropriate way using which we can decide how many features should we keep in our model? Well, there is no thumb rule to determine the ideal number of independent variables, but what we can do is that we can plot the adjusted R-square score corresponding to every iteration. This will help us to minimize the number of independent features in our data while retaining performance of the model as much as possible. So let's just do that. For this, we run the backward elimination again. But this time we pass the minimum number of columns as 1 because we need to plot the adjusted R-square score against the number of features present in the data. To do that, we will use the history variable which contains the adjusted R-square score at every elimination step. We will plot the adjusted R-square score at every step. On the y-axis, we will plot the adjusted R-square score at every feature eliminated, and on the x-axis, we will plot the features remaining at any given step. Plotting this graph has the benefit that we can clearly see how the adjusted R-square score varies with the elimination of the independent features. Now, choosing the number of features we wish to retain can be a very subjective topic. Looking at the plot, we can say that the highlighted region is a good spot to consider if you're looking for the minimum number of features while retaining the model performance as much as possible. On the other hand, if you are looking to maximize the performance of the model and remove only the insignificant variable without harming the adjusted R-square score, this highlighted spot would be the ideal in this case. We can see that the adjusted R-square score almost flattens out beyond this point. Therefore, we can remove quite a few independent variables without affecting the adjusted R-square score. A natural question to ask, which I believe some of you are asking right now, why do we need two methods, forward selection and backward elimination, that do almost the same thing? Adjusted R-square score is indeed a powerful technique, but it comes with one major drawback. It is computationally expensive. That is, it requires a lot of computation power to run. We have been able to implement it fairly easily because the housing prices dataset is fairly small and training a linear regression model is almost instantaneous. For example, our dataset contains 30 columns. Let's calculate the number of models we need to train in forward selection method up to all the features being selected. In the first iteration, we build a model on each of the input variables, which means 30 models. In the next iteration, one column has been selected and we try out its combination with other columns, that is 29 models. And if we generate this, the total number of models that we need to build would be 30 plus 29 and so on till 3 plus 2 plus 1, which is equal to 465 predictive models. If we are using some other dataset comprising of 100 plus features with over 100,000 observations, the process of backward feature elimination or forward feature selection would have taken a very long time to complete. That is why it is good to have a goal in mind that whether you want to have model interpretation as priority and only select a small subset of best features and interpret the model, or you want to strictly remove the features which negligibly add to the model performance. In the first of these cases, we prefer the forward selection as it focuses on choosing the best one first. On the contrary, the backward selection tends to work better in the second case as it focuses on removing the redundant columns first. So depending on our objective, you can choose either forward selection or backward elimination. You can also program both the techniques in a way that the program would auto-stop when the increment in adjusted R-square is less than a certain threshold. Please feel free to play with the code and see what the output you get. Now before we close this module, let's revisit the forward selection for one last time. We have been through some difficult code in the past. This one is no different. I have intentionally left a bug in this code for you. Worry not, you can use this code as it is for the forward selection and the results will be exactly the same. But this bug will affect the overall runtime of the forward selection. It's up to you to find that bug and remove it. Let me give you a hint. We are still building 30 models during every iteration instead of the previously discussed pattern of 30, 29, 28 and so on. Hope this helps. We believe that we have covered the forward and backward selection very extensively. In the next module, we will be looking at our first classification predictive model. But before that, it's time for the module test. Make sure that you have understood all the topics of this module before you attempt the test. Feel free to revise in any case you feel the need to do so.